Okay, everybody, I am right down the hall proctoring the park exam. And so that's why I'm not here. And so for class 2A, you had an assignment that did not get instruction in class because of the 2-hour delay. And when we had off last week, I sent you an email that said you needed to complete the rest of mandatory 4, which would explain to you how to do the green worksheet that I gave you on that 2-hour delay day. So I'm just going to real quick go over that one rule and then move on to the next lesson. This is for 2A only. So if I were integrating e to the 5x dx, here's how I would go about it. So I would look at the integrand. The integrand has e to a power. I know there's a rule for e to a power, so my u substitution would be for that power. And so du dx would be 5, and du over 5 would be dx. So I'm going to do exactly the same thing I do every other time. I get e to the u and then du over 5, which allows me to pull out the 1/5, and the integral of e to the u is e to the u. And so I'm going to get 1/5 e to my u substitution, which is 5x plus c. So 2a, if you did not make a note card with that rule on it, make sure that you do. Make sure that you look at the examples that are on BCPS1. There's no video other than this little piece for e to the u because it's an easy rule. So anytime you have e to a power and it's not that special power like this one, remember, if it's that, then that quantity is equal to u, and I would just integrate that easily using a u to the n du. All right, so the green sheet is on this. That's part of mandatory 4. So during class today, make sure that both 3A and 4A, that you finish checking all of those things on mandatory 4 so that when we have class again this week, we can go over any questions that you have. All right? So I want you to, this is for both classes now, 3A and 2A. So make sure that you know that when I'm integrating, you know this represents the derivative of some function, and the answer to the indefinite integral is the family of curves, right, that has that derivative. And this indefinite integral is an expression, right? And so there is other ways that we can ask that same question, and it's called a differential equation. And a differential equation is just an equation form. And I'll show you what I mean. So a differential equation is any equation that's got a derivative in it. And there are all sorts of differential equations. There's a whole course in it after calculus that's nothing but differential equations. In calculus, we do only one type of differential equation, and I'll talk to you more about that when I see you next class. This differential equation, though, is affectionately known as diffie-q. All right? And so all it means is that I'm giving you the derivative in equation form. For example, dy dx is x. And when I solve this differential equation, I'm still looking for the family of curves that yields this derivative. Now, a differential equation is special because you can get a visual for what the differential equation is, and you can get a visual for what this solution would be, this family of curves that solves that differential equation. That visual, which gives you a picture of the differential equation and then in turn gives you a picture of the family of curves, is called a slope field. And this lesson today is just on sketching the slope field, nothing else. All right, so I'm going to give you this picture of this slope field. Now, I have no idea of why this is crooked. When I scanned the document in, it was totally straight. And so everybody tilt your paper on your desk so it looks just like this, or not, doesn't matter. So make sure that you understand what's going on here. This is just an XY plane. These little dots that look like this are part of the slope field graph paper. And notice I made like an XY axis. Here's Y, here's X. I made the XY axis and I enhanced some of these points. So this is as far out as I want to go on the field today. So here's my differential equation. It says the derivative dy dx is equal to x. That's just a dot. That's one of these dots on the slope field. That's not a negative sign. So this is just x. Okay, just x. All right, so that's a terrible x. There we go. So this dy dx being equal to x simply means, as you know, the slope of the tangent line at every point on the curve is equal to the x coordinate of the point. And so the idea of the slope field is you are sketching at all these different points a little line segment with the slope given by the differential equation. So what do I mean by that? I mean, pick a point. So let's take the easiest point of all, 0, 0. All right, that point is right here. And according to this differential equation, the derivative is equal to the x coordinate of the point, which in this case is 0. So that means the derivative at that point, which is the slope of the tangent line, is equal to 0. And that means at this little spot, I'm going to try to change the color. All right, at this spot right here, the slope of the tangent line will be 0. And so I'm going to draw a little tiny line segment with a 0 slope, because I know all horizontal lines have a 0 slope. And so if I think about it, any point where the x coordinate is 0 will yield a 0 slope. And so all on the y-axis, I would have little tiny tangent lines that have a slope of 0. All right, and so what this is going to do is show me what all the slopes of the tangent lines look like, and what should appear sort of is a picture of the solution, the family of curves that have that derivative. All right, so let's pick another point so we can continue this slope field. Let's pick the point 1, 1. All right, that point is right there. See, 1, 1. Point's right there. And so I know the derivative at that point, according to this differential equation, is always the x coordinate of the point. And so that's going to equal 1. So now here's what I have to do. Let me change the color again. So I have to go to the point 1, 1, and I have to sketch a little tiny line segment with a slope of 1. And so how are you going to do that exactly? Well, you can't do it exactly. You just pick a slant that's comfortable for you. That's my 1. And then I just have to make sure that every other slope that I pick is relative to that one. What does that mean? It means if my slope is 2, it's got to be steeper than this one. If the slope is -1, it's got to be in the same slant but opposite direction. And if it's a slope of 1/2, it would have to be less steep. That's it. Pick a slant, and then everything else has to be relative to it. So I know on this one that every time the x coordinate of the point is 1, and that's going to be all along this line, the x coordinates are all 1. This is 1, 2, 1, 3, blah, 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 that the slopes are going to be 1. So all along that line, I'm going to try to make all the slants the same all along that line. Boom, boom, boom. All right, let's pick another point. Let's pick like -2, 1. So -2, 1, which is like right there. All right. So the derivative is always equal to the x coordinate of the point, because that's what the differential equation. It's all based off of this. So that's -2. So that means I'm going to come over there to my -2, 1, and I've got to make it negative and steeper than that one. So I'm going to go right there. And then I know all along that line, I'm going to get the same slant. All right, so here's what I'm going to do. I'm pausing this, and I want you all to sketch just out here to the edge of the field where I have exaggerated on your paper. I'm going to stop it. I'm going to go ahead and sketch the rest of it, and then we'll come back and compare notes. All right? All right, sketch away. All right, are you finished sketching? Because yours should look similar to what I have here. And if you stand back and look at it, it looks like, if you look at all the slopes, it looks like a bunch of parabolas. Which means if I were to solve this differential equation, I should get a family of parabolas where the vertex, because that's where the zero tangent is, where the vertex is along the y-axis. And we'll talk more about solving this differential equation next class. All right, we're not going to do that now. All I want you to work on today is the sketching of the slope field. Now, when you look at the curve, like this one, I think is pretty obvious that it's a bunch of parabolas. All right? Sometimes when you sketch it, like on the 6 that you're going to sketch today, like some of the curves you're going to recognize and some of them you won't. Why is that? Because some of them you're going to be able to solve and some of them you're not going to be able to solve. So it just depends on the type of the differential equation. And again, we'll talk more about that next time. All right? So let's do one more example, and please make sure that you do this with me. This differential equation right here, this dy dx, is negative x over y. So this one's a little more complicated to sketch because every slope is dependent upon the x and the y coordinate of your point. So notice that I've x'd out 0, 0, because that gives me 0 over 0, which is not going to give me a slope. So let's pick like 0, 1. All right, so if I pick 0, 1, then I know my slope is the opposite of the x, which is still 0, over 1, and that's 0. So I know that on the point 0, 1, I'm going to get a little horizontal tangent. Now, this one's a little different, so just be careful. But every time the x coordinate is 0 and the y coordinate isn't, so that's all along this line, I'm still going to get a 0 slope. So just like the other one, that's going to be true. I just have to be careful that I don't take too many assumptions with this one. All right, let's pick another point. Let's pick on the x-axis. Let's pick 1, 0. All right, so if I pick 1, 0, I get the opposite of the x over y. So that gives me 0 in the denominator, and what does that give me for a slope? That gives me undefined. And what kind of line gives me an undefined slope? A vertical line. So all along this x-axis where the y-coordinate is 0, I'm going to get a little vertical slope, a little vertical line there. Here, 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 here. Just go out to that little 3 by 3. Just go out to the edge of that field. All right? So let me pick one more so that you can see. All right, so let's pick the point 1, 1. All right? So it's the opposite of the x, that's negative 1, over the y, which is 1, that's negative 1. So if I plot the point this one, I'm going to get a negative 1 slope. So that's going to go this way, negative 1. Now I have to be careful because all along this line, it's not going to be the same. It's not going to be the same all along this line because if I pick the point 1, 2, right, then I'm going to get negative 1 over 2. That's negative 1/2, and that's not the same as that. So I have to make sure that I look at that accordingly. So I'm almost out of time. So remember, negative 1/2 is a little less steep than that one. All right, so I'm going to make it a little less steep. Like that. All right, I'm going to pause it. You do the rest, and I'll see you back in a second. All right, I'm running out of time, and also this thing was in my way, so I couldn't sketch everything. But yours should look like a bunch of circles. Do you see the circles? All right, so you're going to sketch 6 of them today. All right, just like that. See,